Hello everyone, and welcome back to a new episode of Advent of Code 2016. We're about ready to get started on day 13 here. I had a look over it before we got started, but I suppose I may as well read it to you guys anyway. You arrive at the first floor of this new building to discover a much less welcoming environment than the shiny new atrium of the last one. Instead, you are in a maze of twisty little cubicles all alike. Each location in this area is addressed by a pair of non-negative integers xy. Each such coordinate is either a wall or an open space. You can't move diagonally. The cube maze starts at 0, 0 and seems to extend infinitely towards positive x and y. Negative values are invalid, as they represent a location outside the building. You're in a small waiting area at 1, 1. While it seems chaotic, a nearby morale-boosting poster explains the layout is actually quite logical. You can determine whether a given xy coordinate is a wall or an open area using a simple system. So you compute this formula based on x and y, add a number that's given to us, and based on the number of bits in the number that are even versus odd, it's basically every location has roughly a 50-50 chance if you assume like all the inputs. I don't know. It's not really chance, of course. It's all well determined, but exactly half of the locations will be odd and half will be even. Is that true? I mean, I guess it's infinite, right? So yeah, probably. Anyway, and so we are asked, given that we're starting at 1, 1, we want to get to 31, 30 in as few steps as possible, according to this rule. So this should be pretty straightforward, right? Let's just grab this number here. And we're not even going to bother with an input text file for this one, since there's really just only one thing in it. Maybe I should. I don't know. But I won't. So there. The first thing to do is to go back to day 11 and grab our search function, because this should implement most of the heavy lifting as like a generic directed search algorithm. Maybe breadth first would be fast enough. I don't know. But we already have a directed search algorithm available, so let's use it, right? And then what we just have to do is model the problem properly. So, well, we need some kind of object that implements the methods that search expects. So let's call it node. And the only thing it's going to store is a tuple, right? Seems pretty sensible. Let's also, by the way, def goal to be 3139, was it? Yes, 3139. 39. That's not def, is it? It's just equals. Okay. And input equals 135658. Oh, apparently input is a special word in Python. It got colored differently. We'll call it puzzle input. There we go. Okay, class node. So, yes, we wanted to take a constructor, init of self, and chord to be, not cores, we're not drinking any beer here, self.chord equals chord. And we want a few methods on this. Notably, to prevent duplicate, we want to be able to store these things as... Oh, actually, it occurs to me that maybe instead of implementing hash and eq, what I should have done last time was have these nodes implement a function called key and just store that key in a set in the search algorithm. That's a little bit simpler. Def unique key of self to just be return self.chord, and we'll just update it here. Unique key equals next.unique key, and then just say if unique key is invisited, otherwise we will visit.add unique key. Fine. So that simplifies things a little. Not a lot, but a little. And what more do we need? Let's say def goal estimate of self is just the sum of the absolute values of the difference between our coordinate and the goal. What is a good way to zip together? I think since there's just two numbers, it's easier to do by hand than it is to figure out a list comprehension with a sum and all that. So let's just return abs of goal of 0 minus self.chord of 0 plus abs of goal of 1 minus self.chord of 1. There you go. That's our goal estimate, our heuristic. Let's def evaluate of self to be. Remember, this is the function where we decide whether it's success, fail, or progress. If self.chords equals goal, return succeed. Otherwise, if now we need to like do some math. We'll def a function here, def wall of chord to be, return true for the moment, and we'll implement that later. If wall of self.chords, return fail. Yeah, that's what we called it, fail. Otherwise, return progress. And we just need nexts, which is pretty simple. Def nexts of self to be is there a good way? Yeah. Node of self.chords. Oh shoot! Plus on two tuples doesn't add the elements pairwise like I would expect. Well, okay. Self dot. Does it matter? I guess we need to decide whether we're storing this as xy or yx. I guess xy is fine. Node of xy for y. Oops, I hit enter there. Y in -1. Yeah, I guess that's fine. -1, 0, 1 for x in -1, 0, 1. Dy and dx are deltas here. And I guess it actually has to be dx plus self.chord chord. Oh, I see I changed my mind about whether it has an s or not. Okay, self.chord of. Oh wait, these are index. The puzzle tells us yes. XY is okay. The left one has to be x. Fine. Plus self.chord of 0. Dy plus self.chord of 1. For dy and dx and all these things. if abs of dy plus dx equals 1. And in fact, we can use a generator instead of a list comprehension. I suppose it doesn't matter because the very first thing this does is iterate over them. I don't know. I guess it iterates over them. It doesn't copy them. It doesn't need them all in memory at once. So why not? Let's use a generator. Okay. Seems fine. Right, and this is the correct condition here. If you add together the absolute values, or if you add them together, the absolute value will be 1 only if exactly one of the two values is 0. I typed a 2 there instead of a 1, silly me. So I think that's right. Obviously, we could be more efficient by like listing the 4 different deltas that are possible, but I don't know, this seems nicer. So now we just have to implement this formula from the puzzle here. So let's just copy this. What do we call this exactly? Oh, and actually, let's xy. Let's destructure it here. I don't know. This is like it's a number, but it's not a formula. It's the result of a formula. Call it arbitrary because it's friggin' arbitrary. And we add puzzle input to it. Oops. And then we'll just look up a formula for counting the number of bits in an integer. The number of bits in integer. I mean, obviously we could do it as in a loop, but there are better ways. Popcount, yes indeed. Python popcount. Okay. Oh, of course, there's a function that's called bin that converts it to that converts a number to binary, and then you can count how many ones there are. You can do it faster, but that sounds pretty good, honestly. Return bin of arbitrary dot count of 1 mod 2 equals, which thing are we looking for? If the number of 1 bits is even, it's open. So if 1, it's a wall. All right, very exciting. Let's print out search of node of 1, 1. That seems like about it, right? Oh, whoops, node the tuple 1, 1, please. All right, does this compile at all? Yeah, compiles. No guarantees. Search of node of 1, 1. Init takes, oh yeah, I did it wrong again already. Look at that, amazing. Iteration over non-sequence, node.next. Oh, I didn't return anything from next. Did I? I did. Why? Node of 1, 1 dot next, please. Here's a generator. Let's make it a list. It's 4 node objects. That sounds pretty good. Let's look at the 0th element and then call vars on it or something. It's a coordinate of 1, 0. That seems pretty reasonable, right? All right, what are you so mad about then? Oh, it has to return how expensive it is to traverse that node. Of course. Right? Is that the idea? Node.next, yes, has to return a cost, and they're all just 1. So let's return 1 and the node. There we go. Let's try the search again. No good. Global name ext. I must have typed it wrong somewhere in here. Yes, next. And parents. Okay. How about now? 96. That sounds pretty good. We got an answer real quick. That's the right answer. Very good. Let's commit this. Day 13, part 1. How many locations can you reach in at most 50 steps? Well, that's totally different. Well, that's interesting. So we could write just a different, We could try to figure out how to trick the search algorithm into not searching for anything, or we could write a different algorithm that's going to loop over the, that's going to just loop over the nodes in a different way than the search algorithm. Sorry, I think I said aloud. The question is, yeah, I did. How many locations can you reach in at most 50 moves? So we could try to tell the search algorithm, hey, you know, the heuristic is always 0, so just search like breadth first for me. But it's yeah. So what we could do to still use the search algorithm and not have to write more code that's going to iterate over our list of nexts is basically have each node record how many times it has, how many moves it has made as another parameter to the node object. And if that value is 51, then it evaluates itself as a failure, as if it were inside of a wall, basically. And then at the end of our search algorithm, just print out the size of the visited set. It's not necessarily the cleanest thing we could possibly do, but it seems all right. It's kind of it would mean that we don't have our solution to both parts in the code at once. And this is a simple enough change that I feel like I should do that. I should make it, I should make them both exist at once. So how exactly is the way to do that? It's not so like easy. Yeah, it is actually. So let's just write another def traverse limit. So we'll write a new function that takes a node and a limit and explores at most limit steps away from the node. So the idea is while limit is greater than 0, well, let's say open equals, actually this is, 50 steps is pretty far. We may have to try a little bit harder to prevent duplicate. Yeah, so what I was thinking was we'll just start with a set of nodes that we can currently get to, and then at every step we'll iterate over all of them and add all of their nexts to the set. And that's fine. But but then, like, nodes that are near the beginning will be getting constantly re-explored over and over. So what we can do instead is have two different sets. One that is all the places we've ever been, and another is the frontier that we're currently exploring at this step. That should limit the amount of re-exploration we need to do. So let's say visited equals set. Well, actually, let's just make it equal to node, shall we? And also we say frontier equals the same thing, node. And the idea is just while the limit is greater than 0, let's see, in 0 steps, yeah, okay, this is the right termination condition. New frontier equals a set comprehension, I suppose. Or lock for lock in locks. So this is like a map cat. It's not exactly great, but for locks in. No, this is not right. Am I? God, I have to write these list comprehensions like what feels like backwards. I have to write all this. Like, I would rather start thinking about it from the outermost loop than the innermost loop. But maybe I'll just do that, and then I'll type some stuff out, and then I'll move the cursor left, and I'll type some more stuff. So what we first are doing is we're iterating over for node in frontier, and then for ignore the cost next in node.nexts for node in frontier. Yes. Okay. And then where does the if go? I guess it goes at the end? Does that mean that Python's list comprehension is always you can only do a filter at the end? So like in Clojure's and Haskell's list comprehensions, you can iterate over a couple variables and then do a filter and then like do some more iterating. You can probably do that in Python too. I just don't know where I need to put the if because it's like everything's written backwards from how I sort of expect it to be. That's my fault, probably, not Python's, but there you go. If not oh, I forgot. We wanted to keep these as a map. What we wanted these mapped. We don't want our visited, our nodes shouldn't, words, don't know how to do them. Our node objects are not currently suitable to be dictionary keys or set members. Rather, we have to store their unique keys. So, node.unique key okay. So now for k node in frontier, how do you boy, Okay, this comprehension is starting to get a little bit out of hand. Let's call this new nodes. And we won't try to deal with getting the unique keys out just yet. We'll just make it a set. We can't because it's nodes, and nodes are not settable. So we'll make it. We'll just make it a generator. In fact, let's not even do that. Let's just. I guess if we're going to do nested for loops, we have to write things not backwards, which is fine with me, I guess. If k k equals next dot unique key. If, let's see, Python dict contains key. How to test if a dictionary contains a specific key. Is it just in? Yes, it is in. Okay. If not, actually, since we're doing this mutably, we're going to need to initialize a new frontier here. New frontier equals a dict. If not k in visited. So here's a new node. We haven't seen it yet. We need to add it to the frontier, and the new frontier, I should say, and the visited set. Visited set of k equals next, and likewise new frontier of k equals next. And finally, frontier equals new frontier. And return visited dot len of visited. How does this seem? Well, it's never going to terminate because we didn't decrease the limit. So limit equals limit minus 1. All right, what else? We will be correctly traversing exactly limit steps. We're going to need to do something. I just am a little surprised, actually, that this wasn't a problem before. If x less than 0 or y less than 0, return true. Apparently, the optimal path, who knows? I'm just surprised that we didn't run into trouble with that part of the formula. The building has walls that we can't travel through. You know, we could inline this whole thing and then turn it into just like return x less than 0 or y less than 0 or this dot count of blah, blah, blah. I don't know. I don't think it's a big improvement. It would be a big improvement in a language like Clojure or something, where having multi-line expressions is a typical thing. But in a statement-oriented language like Python, I think it's often clearer to do things with like if statements and so on, rather than trying to inline it all. Python doesn't really like everything being an expression, and I shouldn't try to force my ideals on it. Okay. Now back to checking this algorithm. Every step we create a new frontier, we iterate over the old frontier's nodes, and for each one check out its nexts. I called this visited set for no obvious reason. Visited, yeah, and so we'll only check each item of the frontier one. Yeah, okay. This seems legit. It seems okay. Let's also print traverse node of 1, 1 and 50. See how that goes. Actually, since we weren't actually running this from the command line, I can just try it here. Int object has no attribute nexts. All right. Why? Why is node an int? Fascinating. Huh. Why is that? What could be? I mean, we can print the node here. It's fine, but I just don't expect that to be anything very interesting. It's 1, right? The only node, the whole frontier appears to just be 1. Am I crazy? Oh, I have to say items or something, right? Because otherwise I'm like iterating over the keys and then destructuring them into a tuple. Is that what's happening? Yes. Stop. All right, let's double check. Yes. Okay, we were making much better progress here. Okay. So let's just get rid of these. 5101. That's not the right answer. It's too high. Okay. Why would this be too high? Visited is a set. Okay, so first of all, is 5101 a plausible number? So that's 50 steps. So the maximum area we could cover is 50 squared, right? We could not possibly get, well, 100 squared, actually. 50 in each direction. And 100 squared is 10,000. Oh, yes, and we covered exactly half of that because we forgot to check if we were walking through walls. Okay, very funny. If next dot no, let's just say if wall of next dot chord continue. $5101. Why was it not 5001? I feel like I did a. We have a. I guess because we have a. We actually have. So if we were allowed to explore 0 steps, our circle would have a radius of like 1 kind. I don't know. It's because we're working with not points, but like grid boxes, I guess. 141. That's uncannily small. I am very concerned by this number. It seems like it should be larger, but I guess actually there are going to be a lot of walls. That's the right answer. Okay, great. We did it. Here you go. Here's the thing that says it's a gold star. I hope you guys enjoy gold stars. And yeah, calendar is progressing. Like I noticed just today this monorail thing. That's pretty cool. I guess that was day 9. Okay, great. So let's just finish things up here. Git add -p. Yeah, let's get commit -m day 13 correctly handle bounds. And let's also, here, this is part 2. Commit -m day 13 part 2. I got that right, yeah, okay. What the heck, we'll push it as well. Okay, great. Well, that was a nice simple one. It was good to be able to reuse some of our stuff from day 11 and have a much less stressful A-star search than the last one. So the reason, I don't know, maybe my search algorithm was inefficient, but it seemed to work fine for this input anyway. But after looking around from day 11, it sounds like there was a lot of domain-specific pruning that we could be doing. Noting, for example, that like if a room contains both a generator and a chip of 2 different metal types, that is, it has 4 objects like A1A2 and B1 B2, it doesn't matter which of the 2 items we move away, right? Moving either both A1 and A2 or both B1 and B2 is sort of symmetrical. And so like stuff like that you could do to trim down the size of the search space, that you shouldn't really expect A-star to figure out for you. Whereas what we had here was a very traditional search with no real way to prune stuff. So aside from the frontier. So that's something that we could have done, maybe, is, we only needed to deal with the separate concept of a frontier versus a visited set because we cared about the size of the search space. In terms of A-star, you don't really need a frontier because you can just search all the objects that haven't been explored yet and not put something onto that set if it has been seen before. Anyway, just a little bit of update on how day 11. By the way, day 11, it ended up taking an hour to finish solving part 2 for me. So, there are people who solved it in a few milliseconds if you figure out all the optimizations, but I don't know, an hour is fine. Anyway, I guess I'm just rambling here. Thanks for watching. Hope you enjoyed, and I will see you next time.